Thomas, hi, can you hear us?
Yes, I can hear you. Can you hear me
Okay.
fine?
Yes, perfectly. Welcome to
Good.
Devoxx.
Thank you.
This is your first time at Devoxx?
Yes, first time.
Congratulations on that. Hope you will have a great
Thanks.
talk. And I know that we will have an interactive contest with you after your talk. So if you have, I encourage everyone to listen carefully to your presentation and to your speech at Devoxx, because after the presentation, you will have Q&A session. And at this Q&A session, all the participants can ask you a question about your speech or your experience, and you will get to the best, you will present to the best questions to the best participants that will ask the best questions. Your book, Cloud Native
Yep.
Spring in Action, right?
Yes, that's correct.
How many books will you present?
We're gonna have five codes to get the book for free, and also some discount code for the others.
Sounds wonderful. With that, I encourage you to start the talk.
Yes, thank you. So, hi everyone, and thanks for joining this presentation. I'm gonna talk about migrating traditional applications to cloud native with Spring. You heard about me, so I'll skip my presentation and move on to how to migrate traditional Spring applications to cloud native. So I assume that you decided for your company or your team to go to the cloud, and you have some existing applications that you would like to migrate to be cloud native, so to take advantage of all the nice features that we have in the cloud. In this presentation, I'm gonna go through five essential migration steps. I'm gonna talk about application servers, containerization, configuration, application lifecycle, and logging and monitoring. Without further ado, let's start right away with application servers. A traditional application in Java is usually packaged as a Word file and deployed to an application server like this. You might have even multiple applications. To reduce the maintenance cost of the application server, we might deploy different Word files on the same one. And with this approach, we have two main aspects that we don't really like in a cloud setting. The first one is that we have a dependency on the application server being available in the environment. And the second thing is that if we have multiple applications on the same server, we are kind of limited in our freedom of making changes. So that could affect our speed, so affecting delivery of new features, because we have to coordinate with other teams and coordinate changes if we want to update the server or making some configuration changes there. In the cloud, to move out from this scenario, we have different strategies that we can adopt. The natural migration strategy, if you start from an application like that, it's moving from an external server to an embedded one. So having the server embedded in your application, and that could be an embedded Tomcat if you were using Tomcat before, or Undertow if you were using something like Wildfly or JBoss. And the Spring Web library helps you with that, providing this embedded server and its configuration. But if you need specific performance, you can also make a further step and go the reactive way. So using Spring Web Flux and relying on Project Neactor and Netty to have a non-blocking server, so that all the threads handling requests will not if they're waiting for some other computation to happen. And that's the case with servlet-based servers like Tomcat or Undertow. But maybe you can also have some functionality that you would like to extract and have it a standalone and go serverless. So without a server, have functions deployed on platforms like AWS Lambda, Azure Functions, or Google Cloud Functions. And Spring Cloud Functions is a library that can help you doing that. We're gonna see more about the first option, and the server part is not enough. The change that we also need to make is about how we package applications, because in a traditional setting, it's usually a WAR file, but now we move to an executable jar artifact. So the 4 applications that we saw before are now independent from each other, and they don't depend on an external server being available in the execution environment. And now let's have a look at a little demo. So this is a very simple application. It only contains a REST controller returning a greeting. And the only dependency I'm using in Spring Boot version 2.4.0 is the Spring Boot starter web. This is the dependency providing the embedded server. In this case, it's Tomcat. That's the default one, but you can also change it. And it works with some auto configuration. So I can go ahead and run it. And now that it's running, I can see that it's running Tomcat, an embedded Tomcat on port 8080. So I can perform a GET request on port 8080, the greeting endpoint, and I'll get the message back. But if we are migrating from a traditional application, we usually have some specific configuration on the application server. So for Tomcat, we might have something like this. This is a server.xml file. It's a standard configuration for Tomcat, where we can define different objects like listeners, connectors, and hosts. When we move to an embedded server, we won't be using this file anymore. But in Spring, we have 2 main ways to configure the server. The first one is through properties. So in the application properties, I can configure different aspects of the server. For example, I can change the port number to 9000. I can define a connection timeout, 20 seconds, and maybe configure also the threads that are used by Tomcat. There's a lot of properties available here that we can use, but sometimes they're not enough. So if your traditional application was deployed on a server that was heavily customized, you can have full control over the configuration of the embedded server by creating a configuration bin. So we can create a class like this. This is configuration. And we can implement web server customizer. This is how we define any kind of custom configuration for the embedded web server. And in this case is Tomcat. There's one method to implement, it's customize. And in here we can basically have the same configuration that is here in Java. For example, we usually have some listeners defined in a server.xml file for Tomcat. We can do the same here in this way. We can add, for example, the version logger listener, which will log at startup several information about the version and the system where it's running. So if I now reload the application, we can see that we have the listener printing out several information about the system where we're running, and the application is also started on port 9000 this time. Yes, and that was it for the first step. In this way, we have a more self-contained application, and we really like this in a cloud environment because we don't want to have external dependencies like the application server. But sometimes also having a dependency on the JVM itself, on the environment, is a problem. So we can go a step further, move on to containerization. With containers, we can encapsulate in the same artifact not only the jar application, but also the JVM and its configuration, so that the application will be totally portable across environments. And the only dependency would be a container runtime, and that would work for any kind of application, not only Spring applications or Java applications. Because once you have containers, you have a standard way of managing applications that is independent from specific languages and framework. For Spring Boot, you have different options to package the application as a Docker image. The most standard one is through Docker files, so writing the sequence of instructions to build the image. But Docker files require certain care in the way that we build images. So some tools have been developed to build the images for us without having to specify the Docker file. One of them is Jeep, that is a tool developed by Google, and it's for containerizing Java applications without the need to provide the Docker file. And we also have Cloud Native Buildpacks, that is a project hosted in the Cloud Native Computing Foundation and can be used not only for Java applications, but for any kind of application. Since Spring Boot 2.3, we have Buildpacks integrated in Spring. So we're going to have a look at that because Cloud Native Buildpacks will take care of all the aspects that otherwise we should consider when working with Dockerfile and Docker images. For example, we don't want to use the fat jar inside the image, but we want to leverage the layered jar mode that since Spring Boot 2.4 is enabled by default, so that we have on different layers the dependencies and our own application code that is the one that changes more often. We also need to maintain Docker files and use up-to-date libraries, being sure of what we use inside the image. We need performance, both at build time and runtime, and security. Containers by default run as a root user. We don't want to do that. These tools take care of that for you. And also, we should never include secrets in an image. Even if in the next layer you remove it, then it will stay in the previous one because it's immutable. That's really important. Let's have a look then at how to containerizing Spring Boot application. As I said, in Spring Boot, since version 2.3, we have Cloud Native Buildpacks integrated. We can configure it. It's available both in Gradle and Maven. In Gradle, we would configure it in this way. It's called boot build image. We can specify an image name. I will use syntax for pushing it to Docker Hub. So I have my Docker Hub username, and then I can dynamically get information about the project name, and the version. And then also important is the version of the JVM that we want to use. In this case, I want to use Java 11, so I can define an environment variable. And in this way, I will get the latest Java virtual machine version 11 available, so with the latest security patches. After doing this, I can run the task. The first time it will take some time to download all the dependencies used by cloud native build packs at the particular implementation used by Spring that is called Paketo. But after the first time, it will be much faster and will take care of all those aspects that I mentioned before, like performance, security, and using layered jars. And that's it. We have an image. And now I can run it. I will expose the application to port 9000. And the name of the image. And here it is. So I can still call the endpoint now on port 9000 and get the reading back. Perfect. After these two steps, you have a fully self-contained and portable application. So it's time to deploy it to a cloud platform. But to do that, you need to take care of configuration first. And the 12-factor methodology defines configuration as everything that changes between environments. And it's something that lives outside the code. So the application package, that could be the jar or the Docker image, will need to stay immutable and portable across different environments. And then we can provide different configuration depending on the environment for each type of deployment. In a traditional application, we usually rely on configuration files that are stored and managed together with the application source code, maybe having multiple files depending on the environment. But that's not a good thing to do in the cloud because we want to have the flexibility. The cloud environment is very dynamic. So property files in a traditional setting will have to be migrated to a different strategy. We're going to still use property files, but in a different way. And we can get rid of XML files like we did for the Tomcat configuration, that we got rid of the server.xml file. And then we also want to get rid of some unmanaged environment variables that we have maybe on the same machine where the application server was deployed. So we want to take back control over those. And we have different ways to do that. As I said, the starting point is properties, again in Spring. But these property files that we have in the source code, we want to use them as specifications for what can be configured in the application, maybe defining some sensible defaults, and have specific values for the development environment. But when we deploy the application on any other environment, then we want to have externalized configuration. It shouldn't be in the source code. We can use configuration services, for example, and Spring Cloud provides integration with different services like Zookeeper, HashiCorp Vault, and Consul. And it also provides a configuration server that we'll see later. If you are deploying your applications on a cloud platform like the ones provided by AWS or Azure, Google, or Alibaba, you can also use the configuration services provided by them. And Spring Cloud has integrations with them, like the AWS Secret Manager. You can use that too. Another option for Kubernetes-based platforms is to use config maps and secrets, as well as environment variables that can always be used. But we would like to have all configuration outside the application and maybe centralized in this way in a configuration service. Let's have a look at how to do that. We're gonna analyze a couple of strategies. So first of all, we want to see how to use environment variables. Earlier, I defined this property, server port 9000. This might be good for my development environment, but when running the application, I might want to have a different port. And for that, I can use environment variables. First of all, I need to build the jar file. After that, is a standard Java application from the Java CLI, and I can specify an environment variable to override that value. Spring allows to use the same naming to override properties. So if I write server port, this will override the property server.port. So I can have maybe 9001, and then I can run the application pointing to the jar file. Here it is. Now on port 9001, we can reach the application. Nice. But in a cloud environment, this is not always a good option. We might want to have external services. So to show you that, let me delete this. We don't need that anymore. But we have this greeting controller that returns always the same message. So we might want to customize this so that it's different depending on the environment. We can define a property with the default value here, greeting, and this will be our default value. And then we can use the abstraction in Spring to get access to it. So instead of returning a hardcoded string, we can return environment.getProperty greeting. At this point, nothing will change because the default value is the same. But now I want to use a configuration server to deliver this configuration to the application. A configuration server is a very small application. The only dependency is a Spring Cloud config server. I'm using the 2020.0 version. And in the Java part, I only have the Spring Boot application class with this annotation, enable config server. That's it. Then the only thing left to do is pointing to a backend that will provide this configuration. I'm using a GitHub repo. So I'm pointing to a configuration repository that is on my GitHub. And that's it. We can run now, not here, we can run the config server application, first of all. And configuration repository, it looks like this. It's a repo on GitHub, and there's an application.yaml file there with a property called greeting and value hello cloud. So if I'm doing everything correctly, I will get this message now when I run the application. So we have the config server application running correctly. In the other application now, I need this dependency, Spring Cloud started config, and I need to specify which configuration server contact. So this is new in Spring 2.4. I can configure that in this file, application.yaml or application.properties, and we can use Spring config import. Then I don't want the application to fail if the configuration server is not up and running, so I will define this import as optional, and then I will point to a config server that is running locally on port 8888. And this would work the same way also for other services. If you have console, or if you have Zookeeper, it works the same. So we have everything in place now, and we can run the application again, making sure that we have the latest dependency with Spring Cloud started config, and then run the application. So you can see here that the first step that the application does is contacting the config server and getting the configuration. Call the application again now on port 9000. We should get hello cloud. Here it is. All right. So far, we have made the application self-contained, it's portable, we know how to configure it in the cloud. We actually have many different strategies that we can use. And we had a look at two of them through environment variables and through a centralized configuration server. But now let's focus on what happens when the application is running. So on the application lifecycle. Here we have some differences between traditional applications and cloud-native applications. So a traditional application, because of the whole application server dependency and maybe multiple applications being deployed on the same server, we have slow down compared to what we can achieve in the cloud. Then each instance, we really take extra care for that because it's expensive and we want to always have it up and running. So if an application is misbehaving, maybe we redeploy it, or if that doesn't work, we restart the whole application server, including all the other applications on that server. And if in increasing workload, we can rely on vertical scaling, so increasing memory and CPU, because sometimes traditional applications are stateful and we can't simply scale them horizontally. This, of course, for cloud-native applications. So when we are migrating existing apps, we should make them disposable and stateless as much as possible. Stateless because we want to use horizontal scaling, and that's only possible if we don't have to manage in a state. And disposable because in the cloud, everything is dynamic, so we can have multiple instances of the same application. And if one is misbehaving, we don't take care of it, but we maybe remove it and start a new one. So they're really disposable. So we have fast startup time because we removed that external dependency, and in general, we have a much more focused application. They are disposable instances. We can start them and stop them whenever the application thinks it's necessary, depending on the health and the monitoring. And then we are allowed to use horizontal scaling. Let's have a look at what we can do in Spring. The stateless part, it depends on what state you're saving and how you're managing it. If it's a web application, maybe you want to use something like Redis for caching or for session management, and Spring has integration to it. But for the disposable application part, we can have some more general rules. Since Spring 2.0, we are allowed to define how the server in Spring should be shut down. So we have a shutdown property that can be immediate or graceful. Graceful means that whenever we stop an instance, we wait pending request to be finished before shutting it down. Otherwise, we get errors. And we also can define a lifecycle timeout so that if, for example, after 20 seconds, there's still some request pending, we just shut it down because we don't want to wait more. And a fast startup time is already there in general, but you can optimize it depending on your needs. Like for long-running applications, like it could be standard web applications, it's fine having a startup time of a few seconds, like we are achieving here with this application. But if you're working with functions, then you might look more into that because a few seconds might be too much for sure. So let's see how this works now with the graceful shutdown. I can start the application again. So we haven't changed anything in the startup. That is now 2.2 seconds. If that is too much for you, there are ways to optimize it, but we are not going to look into that. And the interesting part now is what happens when I stop it. You can see that it receives the shutdown signal and starts doing a graceful shutdown, waiting for active requests to complete. Now, there were none, so it was pretty fast, but it would wait up to 20 seconds. All right. We have gone through 4 steps now, so we have self-contained and portable apps. We know how to handle configuration, and now we also talked about how to make the instances disposable to be managed in a cloud platform with fast startup time, graceful shutdown, and hopefully stateless to rely on the elastic scaling capabilities of cloud platforms. The last step that we're gonna see is about logging and monitoring, because once the application is running, we need to get, of course, information about how it's behaving. This is no news because even in traditional app this, but what changes is how we handle them. Starting from logs, in a traditional app, we probably have log files so that we have applications that have configuration for naming the log file when they exceed a certain size and so on and so forth. And you need this for all the applications. So it's sort of a repetitive implementation that needs to be added to all applications. But in the cloud, we do things differently. We log to the standard output and treating log messages as events. We have an event stream through the standard output, and then it's external tool that take care of collecting those logs and storing them safely. Another difference is about health check. In particular, when the application is live and when it's ready. Liveness and readiness probes is a terminology used in Kubernetes, but it applied in general because it's important to distinguish between these two states that an application can be on. The first one is whether it's alive or not, because if it's not, then a restart might help. And in this case, we know that a restart would mean new instance and destroying this one. But if the application is alive, but it's not ready, then a restart or spinning up a new instance maybe won't help. Think about applications that need a database in order to deliver their services. If the database is not reachable, then the application is live, but it's not ready. So we want to provide information about specs. And finally, metrics. We have a switch from having outside the application some agents collecting or yeah, collecting and fetching metrics. If you think about the application server where we have several applications deployed, we can deploy also some agents on the same application server fetching metrics for us. But in the cloud, we need to get more responsibility as application developers and have something inside the application so that we can look into which metrics we are exposing and how they used, and depending on what is your goal, what you want to monitor. In Spring, we have Spring Boot Actuator that helps us dealing with both the health checks and the metrics, including exposing them according to the Prometheus format so that a Prometheus server can fetch them. So let's have a look. We are still in the same application. We need two things for using Actuator. The first, the dependency on the actuator, but since we also want to expose metrics in a Prometheus format, we need to add this micrometer registry Prometheus library as well. Spring Boot will have some auto configuration when it finds the actuator in the class path, but we should be explicit into what we want to expose. In the application YAML file, we can configure all these metrics and health check endpoints. So starting from which endpoints we want to expose. By default, I want to be explicit into what I'm using. In this case, I want the health endpoints and the Prometheus. Then I can further configure the two endpoints. So for the health, yes, it should be enabled. Maybe if it's a Kubernetes environment, I want to enable the probes. And I want to show details always. And something that I don't like having in it because it's not native is about the disk space shown in the health endpoint. So I will put this to false. And then Prometheus. So now with that dependency and this small configuration, we will have, let me do one thing first. We will not use the config server in this example, so I'll remove the dependency and the configuration so that we focus on the metrics. Let's run the. You can see here that now two endpoints from the actuator are exposed, and we can how they look. So all actuator endpoints by default are exposed through this path /actuator. Monitoring, we can do /health, and you can see both the liveness state and readiness state, or have directly information about the specific state on the liveness and the readiness state. And then we configure Prometheus. So by default, we have several metrics about the JVM, like the memory consumption, the garbage collector. And for Tomcat, we have the sessions, we have the threads that are used by Tomcat, we have the request, different information, the status, if there was any error. But you can add your own, of course, both in the health endpoint. If you want to monitor a specific aspect or a specific backend service, you can add it there, and you can add your own metrics. So what's next? We've been through these 5 essential migration steps, and I think they should be performed in order. The containerization part, I would say that is optional. It depends on how you're going to deploy your application, because if you use something like Cloud Foundry or Heroku, you might want to have just the jar file, and then it's the platform itself providing a container. And actually, it's the Cloud Native Buildpacks tool that we saw before, developed by Heroku and Cloud Foundry and used in their platform, so that when you upload a jar file, then the platform will build the container or image starting from that jar and using Cloud Native Buildpacks. It's important that you don't skip step 1. Sometimes a mistake that is made is going directly to step 2, so containerizing a traditional, meaning that the whole application server is containerized, and that application server includes the WAR files belonging to different applications. And that's really bad, because you are making the whole management of that application much more difficult. So if you don't want to do step 1, I would recommend not to directly move to containerizing everything, because when containerizing an application, we need to have an application with specific conditions. In particular, in the cloud, we can't have applications or multiple processes like the application server and the applications inside the container. It's just a way that is meant to. It would be hard to manage. You wouldn't be able to rely on all those standard and proven practices that we have been developing while using and experimenting with cloud native technologies. And something else is about the 12-factor methodology that I mentioned before. If you're not familiar with that, it's about 12 best practices and development principles that have been introduced by the engineers at Heroku a few years ago, and later revised and extended to 15. While performing these steps, we actually used some of them. For example, we talked about the code base, and that shouldn't contain the configuration. We talked about dependency management, meaning that we want the application to declare its own dependencies, like we have in Gradle the manifest, but we also don't want external dependencies on the application server. Configuration shouldn't be part of it, but should be externalized with special care for credentials and other secrets that should be handled in a very careful way. We talked about stateless processes, finding that it's about exposing the application services through a port, and that application should be self-contained, so like we have a jar file now. Concurrency, of course, is about this explicitly, but it's allowed. We have a web server with multiple threads. We can go on with that. And disposability, we talked about that. Environment parity. With Dogger, we have an application that is portable everywhere, so we can have as much as possible similar environments. We talked about logs and telemetry for metrics. So if you're interested in cloud native applications with Spring and Kubernetes, as mentioned before, it's called Cloud Native Spring in Action. It's available right now in early access on manning.com. Here is a % discount code that you can use not only on my book, but in for all products in the catalog. And later in the Q&A session, I'm going to raffle 5 codes for a free ebook. Now, in the last minute I have, I prepared a bonus demo since we talked about Kubernetes. So with the same application that we achieved after performing those 5 migration steps, we can now deploy it in Kubernetes. And I have a deployment file where I can specify that I want 3 replicas of that application. This is the image that I built before. I define the port, I define the liveness probes, and I also overridden the reading property through an environment variable. I have Kubernetes running locally, so what I can do is running those files. So I have an object for the application and the service object to expose the services. I'm using Minikube for that. So you can see that the applications are live now, but they're not ready yet. Readiness probe. So let's wait for them to be ready. And once they're ready, we can call the endpoint. Ready now. Well, that's taking some time. Yeah, the power of live demo, right? Well, something is, of course, wrong. If I can fix it quickly, otherwise. Uh, Yes, sorry for this. Not the perfect ending, but yeah. So thank you for joining. I hope it was interesting. I can meet you in the Q&A session later. So if you're interested, if you have questions, just join there. And you can also join the raffle for 5 codes to get a free ebook.